Hello everyone, thank you for joining this talk, which is going to be on the importance of considering multiple sea state realizations when estimating design loads. I'm Andrew Cornett, and together with my co-author Scott Baker, we're both with the National Research Council of Canada. Here we can see the outline for the talk, so we'll begin with the motivation and objectives, then we'll focus on a scale model test case study of an exposed offshore marine terminal. We'll look at the scale model setup, we'll look at the extreme wave conditions, the global loads on a gravity-based caisson structure, we'll look into the assessment of repeatability and variability, and then wrap up with a few conclusions. The motivation for this study stems from the reality that establishing design loads for complex structures in near-breaking, multi-directional shallow water wave conditions is extremely challenging. Not only do you have uncertainty in the wave conditions themselves, but you have the added uncertainty of the relationship between the waves and the forcing. So the objectives of this work are really to explore and quantify the repeatability of wave statistics and global loads, explore and quantify the variability of wave conditions and extreme loads measured in different realizations of a common design sea state, and finally demonstrate the importance of considering multiple sea state realizations when establishing design loads. The model test case study concerns a 45-year-old marine export terminal comprised of equipment's topside supported on several gravity-based caissons. And the objective of the study was to establish local and global wave loads on the caissons and the superstructure to support an extensive upgrade of the facility. Let's now look at this site in a bit more detail. We're focusing on this particular berth, the north berth at Terminal A. And in this dredge navigation channel here you have a 15-meter local water depth. You have at the site design water levels up to +8 meters. You have design wave conditions up to HS 7 with peak periods of about 10.5 seconds, approaching from the west and the northwest directions. And these waves have to propagate across a broad and shallow foreshore where the water depth is about 13.3 meters. And so this foreshore and its effect on the waves has a big influence on the wave conditions at this berth. Let's now look to the layout of the model. This red rectangle here shows the outline of the 50 by 30 meter directional wave basin where the model tests were done. Our scale was a length scale of 1 to 35. Froude scaling was used. And we had realistic reproductions of the bathymetry and then the caisson structures at the berth of interest. All our tests were done using short-crested multi-directional waves. We modeled 4 different gravity-based structures with their topsides. We measured global loads on 3 of the caissons, and also the pressures on the surface of the caissons at over 30 different locations. Here you see a picture of the model or the wave basin during the wave calibrations at the beginning of our study. Here you see the 3 of the caisson structures. You can see they have this kind of square or rectangular base below the waterline on which you have these 4, 1, 2, 3, and there's a 4th one back here, 4 different columns, square cross-section columns rising up, supporting this rail here. So this is 2 rails, one in the front, one in the back, supporting a huge crane which travels atop these rails. And then here you see a model test in action with water in the basin, the waves being generated, propagating, and then interacting with these caissons and the topsides. Let's now look to the wave conditions and the test program. So our wave conditions corresponded to average recurrence interval events of 20 up to 1,000 years, approaching from three different directions. And for each of these different wave conditions, we generated three different 2-hour-long realizations. And we did this so that we could investigate the natural variability of Hmax and Etamax, and also the implications of this variability on the maximum pressure, moment, and force. We looked at four different model setups. In configuration 1, the structures were complete, and then in the other configurations 2 through 4, we removed portions of the topsides. And then in total, so that gave us 135 unique model tests. Let's now look to the ratio of Hmax to Hs. At the beginning of the study, there was quite a bit of uncertainty concerning maximum wave heights and crest elevations at this site due to the kind of unknown effects of this broad and shallow 13.3 meter depth foreshore. So wave data from the model was actually used to confirm Hmax HS ratios at the berths, and this led to a revised numerical mid-ocean study being undertaken to finalize the design wave climate. So here in the table you see an example of some of the results for ratio of Hmax to Hs. So you can see at a single location we have ratios ranging from about 1.45 or even less up to a maximum of about 2.2. So this is indeed a very broad range of Hmax over Hs. So let's look now to the repeatability and variability of the waves. We have here results for 6 different tests with a 500-year ARI seastate, and over here 6 other tests, 6 more tests with the 1,000-year ARI seastate. So the 2 bars in blue are 2 trials of the same seastate realization or the same wave train. In green you have realization number 2, and then in sort of pink red here you have realization 3. So you have 3 different realizations, each repeated 2 times. So from kind of looking at this results here, you can conclude that multiple trials of the same seastate realization are highly repeatable, except perhaps for the Hmax value. Different seastate realizations, called seeds here, give very similar HM0 and even H1%, but there are significant differences in Hmax and Etamax, which we see here. And Hmax to HM0 ratios for these tests range from 1.6 to 2.0 for the 500-year wave condition, and from 1.5 up to 1.9 for the 1,000-year wave condition. Let's now look a little more detail at the peak force. So here we have a typical force time history here, measured over a 2-hour-long test. Used a standard peak over threshold analysis to identify the local maximums in the record, and then from those create probability distributions. So you see 6 of those plotted down here. So these are for 3 different realizations, each repeated 2 times, trial 1 and 2. So then we have our 6 test results here, and so you can see we're most interested here up in the extreme values, the upper tail of these distributions, and in this case we have quite a range in the maximum values. So I just want to mention these various extreme value statistics here that we're going to talk about. We have the maximum value, which is clearly the single largest maximum value recorded over the 2-hour test duration. We have the 99 percentile value, which corresponds to the 99 percentile value of this cumulative probability. And then we defined in this study two other values, the top 5 value, which is really the average of the 5 highest peaks, and then the top 10 is the average of the 10 highest peak values. So let's look now to the repeatability and variability of the loads for this 500-year sea state. So we have again, two repeats of the same wave train in blue, two repeats of a different wave train in green, and then two repeats of a third wave train here in the red and the pink. 500-year wave condition on this side. This is the force, and then the moment, so over here. So can conclude that peak loads and moments are clearly less repeatable than the H max and the eta max. Can conclude that different sea state realizations lead to a wide range of maximum forces and moments, and it's clear that less extreme quantities like the 99 percentile value or the top 5 or top 10 value are more stable and repeatable than the maximum values themselves. Here we have results for the 1,000-year wave condition. Again, peak forces on the left and peak moments on the right here. So we have again can see that different sea state realizations produce a wide range of maximum forces and moments. So we have comparing this with this, or values up here to values down here. Less extreme quantities like the top 5 and the top 10 are more stable and repeatable. So if we look to the top 10, it's very repeatable. And then the variability between different realizations is also much less than the variability of the maximum force value over here. And we can conclude or see that the peak moment is more variable than the peak force. Now we come to our conclusions. We've seen that wave conditions are in general highly repeatable, but it's important to bear in mind that different realizations of a sea state can produce very different maximum wave heights and maximum crest elevations. In our case study, we had a very complex relationship between wave conditions and loads. So we found that, or we saw that small changes in the crest elevation of the waves could produce some very big changes in maximum force and maximum moment. And this depended on whether or not the wave crest impacted against the rail and the top sides above the caissons. So we've seen the different realizations of a sea state can give very wide range in maximum forces and moments. As a result of this, we feel that conducting tests with different time domain realizations of the designed sea state is strongly advised in order to develop reliable estimates of extreme loads and the moments and their variability. Repeating tests with the same wave train is essential to assess repeatability. And finally, scale model tests are very useful and helpful to establish design loads for complex structures and complex cases. Thank you very much for your attention, and I'll do my best to answer any of the questions you may have. Thank you.